Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello, I'm happy to present Michael Kaufman, who is a professor at the University of Tübingen. Michael's interests are mainly in graphs with visualizations, on graph drawing, and algorithms and their complexity, and in many other things. So I hope you will enjoy the talk. Please, Michael.
Thanks, Dev. It's a pleasure for me to be here. Thanks for the invitation. I will talk about map labeling with leaders. Map labeling is a very traditional and old problem, how to label map, how to put text on maps. And I will talk first about map labeling and review the traditional style, and then I go to map labeling with leaders, a special model that kind of we invented. And we are a core group of Michalis Bekos and Antonis Symphonis from Athens in Greece. And we did this work in the last 5-6 years. And part of the work was also done together with these 4 other people. And the first paper, for example, was shared with Alexander Wolf from Karlsruhe, and the last one by Martin Nöllenburg, also from Karlsruhe. And the other 2 people from Greece, they also shared some of the work in the middle. So what is map labeling? Here's the traditional problem. You have a map and you want to label, it's a map of France, and what you want to do is you want to label some regions of France, and the way to do it, a very simple way, is to put a point somewhere in the middle of the regions, and then you place a label next to the point. And the rule here that I applied was to place these labels always in the northeast corner of the point. Okay? The problem that you also see already is that some of the labels overlap, and that should be avoided. That's the map labeling problem, that you want to avoid cluttering of the labels. So as I'm mainly algorithmic oriented, I will restrict on very simple mathematical models, and I won't always try to achieve optimal solutions, and my goal is always to find efficient algorithms to find such solutions. Okay, and here's again the model, the simple model for map labeling. So what you normally model a label by a box, and the box is attached to a point, like here. So you have 4 points, A, B, C, D, and you can attach the text in the northeast corner. It would look like that. Then you see certain overlaps here. Okay, that's the one pos problem, the one position problem. But of course, you can also extend this to 2 positions, or 3 positions, 4 positions. There are several models there. 1 pos and 2 pos models are the most simple. So in the 2 pos model, for example, you have 2 possibilities to place the label. Yeah, But let's come back to the one-post problem. And what you see is that the label of A and B would overlap, so you can only place one of them. Okay, and you model this by a conflict graph. So you say vertex, you have the vertices A, B, C, D, and two labels are in conflict, they overlap. And then you solve a maximum independent set problem. The maximum independent set problem places labels on the vertices of this graph, such that at each vertex, at each edge, there's only at most one label. And that resolves all the conflicts. And the maximization problem here, of course, has the goal to maximize the number of labels that can be done here. For example, you could realize the labels for A and D, or for B and C, but nothing more. So that means here you shoot for a maximization problem. But of course, maximum independent set is in general NP complete, and also for this kind of graphs, it's NP complete. And therefore, people use heuristics or approximations and exponential time algorithms to get solution. Okay. Yeah, so this is a very simple and basic model. But what we want to solve is such problems. And that's the map that motivated our research. That's a map of Greece, and it shows the infrastructure of the Greek school system. Oh, and what you see also, there are a lot of labels, and labels are attached. Here is Athens. Here. Labels might be attached to cities, like here or there, but they also have as attachments big label blocks. And of course, such blocks cannot be attached to the city. And therefore, you place them somewhere else. And the designer here, well, for Greece has lots of sea around, so there's space to place the labels somewhere around. And the labels, you see, the labels are connected to the cities by polygonal segments. And these segments will be called leaders in the following. Okay, so that was our target, to label such maps automatically, to find algorithms for such maps. But of course, we are, we started with very simple mathematical model that we could, where we are restricted on some basics. And this is here. The first model is that we say we have a rectangle, and the points that have to be labeled are in this rectangle, and we consider only that we say all the labels should be outside of the rectangle, and here we say let's restrict on the case that they are on the right-hand side. Okay, so we invented two different kinds of leaders. We wanted to have. I will talk here only on rectilinear leaders. We also have had other kinds of leaders, but here I want to talk only on rectilinear leaders. The first is OPO kind of leaders. OPO means orthogonal, parallel, orthogonal. So it's each leader consists of, let's say, 3 segments. So the first segment is orthogonal, runs orthogonal, horizontal, or orthogonal to the side where the label is, and then a little bit in parallel, and then again a little bit orthogonal. So it goes straight to the boundary, and then there's a little routing problem to be solved. For PO leaders, it's a little bit simpler. So we have each leader has only 2 segments, vertical and horizontal in this case. Of course, the labels have to be disjoint. They have to lie outside but touch the boundary, and so on. Intersections of leaders with other leaders are not allowed. So we don't want to have crossings. Okay. And we might prescribe ports where the leaders touch or not. So again, 2 different models here. So let's come to the first algorithm. Here's an example. So we just consider the problem OPO leaders connecting labels to one side, like here, and the labels have uniform height, like this. Okay. So and here you see a solution. Maybe it's not so visible, but of course. So what's the method to do that? We want to have. I remind you. What is the method that avoids crossings of the leader? Well, you start here, assign that label at that point to the first label, the second to the second, the third to the third. Very easy. So you just do a sweep line. Okay. Again, summary of this algorithm. The model is you have a fixed size and fixed ports for the labels. The goal is to find a feasible solution, just a solution, no real optimization. And the method is just a plane sweep from top to bottom, from bottom to top, whatever. We did always from bottom to top. Okay, so that means you connect the ith lowest point to the ith lowest label. Okay, back. And well, to do that, you just have to sort, and then you assign that. Running time is n log n. Okay, that was the first algorithm. Now here's the second. The second algorithm, we want to now minimize something. And what we want to minimize is the number of bends. You remember OPO has 2 bends or 0 bends. If it goes just straight, in the last example there were many leaders that just went straight to the label. I was lucky. Here we want to minimize the number of bends. And that means we maximize the number of straight leaders, because it's either 0 or 2 bends. And well, we consider the model that the label should have uniform height, let's say h. They should all have the same heights. And the method is dynamic programming to do that. You can do it efficiently by dynamic programming. So you define S of Ki. S of Ki is, okay, I should draw something here. So what you have is a set of labels on the right hand side, and well, if there's space, then you are allowed to do that, to have some slack here. But what you want to control is this height. That's what I call stack, because the labels stack on top of each other. And this is S of Ki. So you look at the K lowest points, if there are K points here. So this is the first one, this is the second one, this is the kth. And if you compute the lowest height, where for the first K points, you have I of them are straight. So you save 2I bends. And how do you do that? That's here. So the lowest, to place the lowest, the lowest label, it just goes on at the baseline. The label has height h. Okay, so S of 1, 0 is, so no matter what you do is just place it here. And if 1 is up here, then you cannot do a straight. And that means, so 1, but no straight. The next is 1, but 1 straight. So either if 1 is down here, then the first is here. But if it's here, then, and this should be straight, then you move that label a little bit up. But only to this point. Okay? And that is, this height is y1. So it's the y coordinate of the first point. Okay? Good. And then we go to the recursion, and the recursion is the following. So what is Ski? Or let's say we have already Sk minus 1, and we consider now the kth point, which is here. Okay. Well, if we have already I straight here, then we just place the kth label on that, on top of this, of the lowest. That is this. Sk minus 1. I plus h. That's the height. Yep. If not, if we have, then we compare this. So this solution, where we have that, to the other solution where we have here K minus 1, I minus 1. That means this kth should be straight. And you place it there. And that's, well, you compute this, you go to yk minus h, and then you add a plus h. on top of it. And that's it. That's all. So that's, here you have your recursion, and then you just fill the table. It's a two-dimensional table.
So what's the complexity here?
Well, you start here, and then you just compute these numbers. K runs from 1 to n. I runs from 1 to, at most, to n.
Is it n squared then?
It's n squared. At the end, you would have S of n, comma n. So you need so many entries. Okay, that was the second algorithm. Now go to the third. Third algorithm is, let's allow labels on two sides. Okay, now we know how to do it on one side. OPO, now we say, well, two sides. But very simple model. Let's say we have labels of maximum height such that they just fit on both sides. Well, how would you do that? Well, you just have to decide on which side the leader goes. You have to decide that this leader, the Sicily, goes, the label of Sicily is on the left-hand side. Otherwise, it's on the right-hand side. So you have to, somehow you have to split the set in two parts, and then you solve two independent problems, right? Well, that's easy. So what you can do, just move here, go to such that n half on that side, n half on that side, and then you just do that. But maybe it's not optimal. As you see here we solved the maximization problem. Namely, we want to minimize the total leader length. Okay. For example, here in Italy it's like a diagonal, right? So many points on the north are on the left, and in the south are on the right. And if you would split it exactly in half, then points that are here in half, that are in this area, they would be connected over there. And that would make a very long leaders. And we want to avoid that. Right? And to do that, we also use dynamic programming. And here we just say L of Ki is the minimal length. So we sweep again from bottom to top. Consider the kth lowest points, and we say this is the minimal length, where for the kth lowest point, I of them are on the left-hand side, the others on the right-hand side. And then, therefore, we compute the solution of minimal length, and then we add a new one. And well, the formula, the recursion is very similar to the other one. So we just fill a table for different values of k and I, and the running time is O of n squared again. Okay, third. Now fourth. We allow labels on all four sides. Part one is, well, I suggested that already. Before we had Italy, and we just divided the set of points in two parts, in two sets. The points that go, those leaders go to the right, and the others go to the left. Here we would have four sides, so four sets. And there we have to be a little bit more careful because the leaders, some leaders go horizontal, the others go vertical. If they go to the top side, labels on the top, they have to go vertical. So, but then we have to avoid that vertical and horizontal leaders cross. So that means we have to partition the problem, the rectangle, such that you have to partition the rectangle such that in something like this, such that here they go to this, here they go to this, here they go to the bottom, and here they go to the left, such that here we have n over 4, let's say n over 4, and just assume that we have n over 4 labels on that side, on that side. So we have to partition it in that way. And the right formulation is that those areas, those regions should be convex. But that can be done by a rotational sweep of this to find. This is not straight. So imagine that those points are sitting all in here. Then it's much harder to split it in four parts. So, but it can be done in n log n time. But here I want to show something else. So that's actually a map from a website of Karlsruhe that shows the some addresses, some locations for daycares for children. So, and there are 8 such daycares in Karlsruhe, and the guy who designed this just placed you really can see it, just placed the addresses around the map, and then has drawn this to the locations without thinking anything. And therefore you get a mess. Many crossings and you cannot see anything. And he even forgot one line. So I think he forgot this one. We solved it optimally, and it looks like this. And optimally means also with minimal total length, leader length. So here we had, in this case, we had only feasible solution when you partition.
But so you didn't use the left side over here? Or
Yeah.
you did not?
No. We just say keep it on 3 sides. But the method that we used is the following. We formulated this problem as a matching problem, bipartite matching problem, as follows. So in bipartite matching, you have 2 sets. One set are the locations of the daycare, of the points, right? The coordinates. And the others are the labels. But you don't know to which label the points will be connected. So, but you know where they are. That means you can, if there is a leader from here, from that point to this leader, then it will cost you. Then this leader will have that length. And that gives the graph. So you have the labels and the points, and you have edges of potential leaders with weights of the length. Then you do a minimum weight bipartite matching. Very easy. Conceptually, very easy. And that can be done, and you have to prove, of course, that the solution is crossing free. It's not trivial to prove that, but you can do it. And with Weidjar's algorithm, this can be done in O of n squared log cube n. Weidjar's algorithm is for matching problems in geometry, in the L1 norm, in the Manhattan norm. Yeah. Okay, let's come to PO leaders. PO leaders, again, as I said, we have, it's on the right-hand side. So here I have the OPO solution and the PO solution. Okay, and the first observation is there are non-unique crossing-free routings in PO. Okay, in OPO, it's clear, it's unique. So you just go to straight to the right-hand side, to the boundary, and then connect it crossing free. So the lowest will go to the lowest, and the second will go to second, and so on. Here, you see that the second point is connected to the third label. Although you will see that it could be different. Namely, what you do is just take the OPO solution and you flip the first two segments. Okay? If you have an OPO, looks like this, then you do flip these two segments to here, and that saves one bend and gives an OPO, an PO leader. So, but in that case, the second would be connected to the second point. No, but as I state here, you might create crossings by that operation. How is this possible? Well, if this is here, okay, and you would do the same. So 1 goes to 1, 2 goes to 2. And you create a crossing here. But you can resolve that by saying 2 now is assigned to 1, takes this label. And that one takes this label. That's resolution of crossings. So, but you have to do it several times, n squared times, eventually. And that leads to a crossing-free solution. And here's an example. It's actually a nice application. In medical maps, you often find labelings of this style. And it says n squared. Use n squared time algorithm. Okay? And if you know that, you can do everything, all the algorithms that I had before, the 4 algorithms, you can do now for PO, the same. So now that means we have 8. So here are the theorems, corresponding theorems. So for the minimal total leader length, and here it's for the two sides. You can do the same with PO. And I will just show the example, the corresponding minimal total leader length for PO and OPO. So PO is here, OPO is here. And, well, which one is better?
I think on the left is PO, right?
The left is PO, right?
They have less turns.
Yeah, of course. I mean, they only make one, at most one bend, and the other makes normally two bends. And the bends are in OPO are very close together. But what is not so good in PO, but for this example it doesn't matter, is that you have additional vertical segments within the map.
Yep.
And here you just go straight outside on the shortest way outside, and you don't disturb much. So
It should be.
it's not clear.
The user study is needed.
Yeah. Okay. Yeah, we extended this to, well, we said what will happen if we don't have space for just one on one side. So you would have two stacks. Can you do that? Can you do the same? The answer is yes. You can still do dynamic programming, and you can do that again. But the complexity is much higher because the dynamic programming is much more complicated. And we can even extend this to 3 stacks. And we even can say, well, if you use, let's say, the second step, a stack for your label, then the rule should be that the bends are next to the stack. So it's clear that these bends that use this are here, but the bends to that label could also be here. Why not? And we say no, we don't allow that. But this also works. Okay. Another more general scenario is that you don't have points, but polygons, if you want to label some regions. Like this is Germany now. And what we do here is, well, we formulate it again as a bipartite weighted matching problem, and we abstract such a complicated region by a rectangle, by a large rectangle, and allow to have the point somewhere on the boundary of this rectangle. Okay, and then, well, then if the label of Bavaria, this is Bavaria, is here, then it's optimal to place the point somewhere down here, because then the leader is very short and straight. Okay? So in the weight, there you have to compute the minimum Manhattan distances between the polygonal region of Bavaria, of this rectangle, and that one, and that label, and or that label, and that label, and that label, in the formulation as a bipartite weighted matching problem. But this also works. Okay, next. The next is, here's the motivating example. It's from the Deutsche Welle TV weather forecast map, and you see that the points are that somehow they used diagonals. So not straight and then these two bends and so, but one bend, but with a diagonal segment. A diagonal segment and a straight, a horizontal straight. So, and that was not introduced by us, but by Bankert et al. But we adopted Martin Nöllenburg from this group that invented that and extended that problem. The problem that they couldn't solve is the following. Imagine that the cities of South America are all at this point, somewhere here. Then you cannot connect from here to down there. It's not possible. If you do just diagonal and straight, it's not possible. Therefore, we extend this with the following. So we allow three kinds of leaders, namely O, D, P, D, or DO. DO. And if you have only these three, so it's still the angle is not sharp. There's only one, and you have a diagonal into it. And we could prove that if we only use two kinds of leaders, namely DO and PD. Go back. DO is this, as before, as in the example before, and PD, this. So if it's too close, if this point is too close here, then you use PD. Then it works. And in O of n cube time, you can do almost everything. Minimal total length, leader length. But it's very non-trivial, the crossing resolution phase. Okay. Another variant was done by Lin, Cao, and Yen, not by us. So this is not our work. This is Taiwan, and these are birds that occur in Taiwan. And there are 8 different birds, but they occur in many different places. So they consider many to one labeling. Okay. So, for example, hawk has 4 positions. Well, and there you come back to, you can take rescue in graph drawing. In graph drawing, you have such a problem. Namely, you have what you have here is you want to minimize the number of crossings in a 2-layer scenario. So you have 2 layers somehow, and this somehow is fixed, and you want to rearrange these labels such that the number of crossings is minimal. And that's, of course, NP-hard. And they propose heuristics for it. Okay. Let's come to my last scenario, and that's mixed labeling. So now we want to, so we had this inner label, this traditional label. That was my introductory example. And now we say, well, if we have clutter, if we have overlap, we cannot avoid it, then we use boundary labeling. But only there. If it's only if it's necessary. So we mix it. And we just take a very simple model, one position, northeast corner, and OPO leaders to the right-hand side. And this gives that solution without cluttering. Quite nice, I think. Although, yeah. Well, why do you need, for example, these 3 leaders? I mean, in the middle area, you had only here this cluttering. So if you have clutter, if you have overlaps, then you have to use a leader. Well, at least one. Okay? And then, well, which one would you take? Let's say this. Then it crosses, this leader crosses something else. And then that makes, yeah, this and then this. Domino effect is the right word for it. Okay? But let's consider these 2 labels, Pays de la Loire and Centre. Which one would you take to be a leader?
Which is closest to the right.
No, that's not the right answer. If you would take this, the topmost of the 2, it would cross the other one.
Yeah.
So that would cause that the other is also a leader. Then you would have 2 leaders. That means you always have the lowest as a leader, and the other you don't know. Maybe also by other reasons. That's a rule. So here's the model again. You have A, B, C, D, inner as inner labels. So you have the rectangles and the leaders. I just have drawn the first segments, not the others, because now it's clear. Here's the solution for it. So you can realize only B as inner, because, well, and here, yeah, here's the observation. If you have 2 intersecting boxes, assign the leader to the lower of the 2 intersecting, of the 2 points. Here, for A and B, well, if A is an inner label, it intersects B. No matter if it's inner or leader. So it cannot be an inner label. It must be a leader. And of course, this leader destroys that one and that one. And that gives immediately that. Yeah, and that's the crucial observation here. And then you just do a plane sweep. And you say, well, for 2 intersecting boxes, you apply that, assign a leader, and if you come down and you have not assigned a leader to a box, then you can place the inner box there, and you just go from top to bottom in time n log squared n. And log squared n because you have to solve intersection problems in geometry in the plane. So that's if you go to the right-hand side. If you go to the left, then the thing stops. It's not true anymore. The observation is not true anymore. It's not symmetric. because the point is not in the middle, but at the left. So you cannot say that, well, the top, just draw the leader to the left, but the lowest of the two. It's not true. That's a solution. So, and there we didn't manage anything very good, but maybe it's not possible. We don't know. So we applied a divide and conquer algorithm, and we succeeded with n to the power of O of log n, which is still sub-exponential. Actually, that's an amazing result because the maximization problem of inner labels is NP hard. If you maximize the inner labels plus the leaders, you can do it in sub-exponential time. Okay. Conclusion. Well, what did I show? I've shown a nice playground for algorithms to work with, that we developed. We developed plane sweep algorithms. We developed bipartite matching algorithms, and so on. Of course, dynamic programming, divide and conquer, a wide range of algorithms could be applied here. I learned dynamic programming. Before I knew how it is done, but I didn't really apply it. And I really had to, we really worked hard with dynamic programming. What is open is better algorithms for the mixed model. I think we wanted to come closer to, well, what we had before, and that was a mixed model. Actually, you should not use boundary labeling. If you could apply, if you have space in the middle, that you can place the labels inside. But if there are many points and the labels are too big, then you should use the space outside at the boundary. And therefore, well, we did a whole range of generalization, but we still didn't manage to do this, our old motivating blue map. I mean, here we don't have a rectangle, but the boundary is somehow a polygon. And we don't have nice stacked labels, but these labels are very much distributed. And sometimes they take also care of the islands of Greece. And it's still challenging. There are more challenges inside of here. Okay, thanks a lot. That's the end of my talk.
Thank you very much. I have a question. So what the approaches seem very practical. So were they implemented in somewhere?
Mm-hmm. They are implemented. These, what you have seen.
In some, are these industrial tools?
No. Just.
I see in your.
Yeah.
Another thing. So what is your observation? Is it easier to work with diagonal leaders or rectilinear leaders?
Graphically more appealing are diagonal leaders. But yeah, but to compute them or to resolve the crossings, it's much easier to do it rectilinear. You have to put much more effort. and you do it diagonally.
I have no more questions, so just thank you.
Thank you.